Okay, thanks for this opportunity to share my work. So this is a joint work with my PhD supervisor, Huanchen Bao. So to start with, I will give you recall you what is a quantum group. So basically, the starting point is that we were given some data. Say let's G be a complex connected reductive group, define a complex group. So for example, we can think about GLNC. Then we take a maximum torus and a Borel subgroup T, which is contained in B, and we consider whether X be the character lattice and Y to be the co-character lattice, and we also assume this alpha I. So this I is just an index for the simple roots. So we assume alpha I is simple roots and alpha I check is simple co-roots associated to this Borel. So given such data, one can consider a quantum group. So you construct some associative QQ algebra, which is defined by some generators EI, indexed by the simple roots and Fi, and also the Cardan part K mu, which is indexed by the co-character lattice and modular some relations. So this is a non-commutative of the algebra. You have some product here. Okay, so then I want to talk about the briefly mention the canonical basis. So when I talk about canonical basis, I really mean the canonical basis on the modified quantum group. So modified quantum group is basically that you replace your Cardan part by some idempotents. So this is a U dot. You have it's a direct sum of all these things. And you have we use this notation B dot to denote the canonical basis of U dot. It's really just some very nice basis of this modified algebra. Then we assume this A to be this non-polynomial ring ZQ with QQ inverse. We can consider this. So this U dot has a nice integral form, which is spanned by this canonical basis. So a priori, this is just a module, but actually one can prove that this is more of a subalgebra. So we can also see that so this U dot A is generated by some divided powers as subalgebra, but this is actually not very important in this talk. Sorry. Okay, so the point is the point is that one can use this integral form to construct the so-called Chevalley group of some to construct this Chevalley group. So by definition, a Chevalley group is a split reductive group scheme over Z. Or you can think of this in the following rather vague definition. A Chevalley group is some properly chosen Z form of your complex connected reductive group. So these groups are some classical objects which were considered in the last centuries. So first considered by Chevalley and then reconstructed by Constant. And more recently, Lusztig gave another construction using his theory of canonical basis. So actually, it's Lusztig who first proved that this construction, this coordinate ring of this Z group defined over Z is geometrically reduced. So, namely, you do not, after doing base change, you do not need to take reduced part. It's always reduced after base change. So next, I'm going to recall you what's the basic, the brief construction of Lusztig. So we just, this is a notation. So basically what you do is that you have an integral form in your quantum group. Then you just do specialization, you send your Q to 1. That's the basic idea. So here for any commutative A with unity, we apply base change just by sending Q to 1. We consider this U dot A. And we also use this B dot to denote the canonical basis in this base change algebra. Then we consider some kind of restricted dual of this dot algebra. So basically, a priori, it's just some A sub module. So it's an A sub module of all the A linear forms, but we consider those which are spanned by dual canonical basis. So meaning that this dual canonical basis is just, so in other words, you consider this is an A linear form which vanishes on almost all the canonical basis elements, just except for finite many ones. Then you construct this OA, and you can do base change. You can see that this OA is actually, in some sense, defined over Z. Everything is base change from some algebra defined over Z. So then Lusztig showed that this OZ actually gives a defined Chevalley group. And for any algebra closed field K, if you do base change to this thing, this OK is isomorphic to the cardinal ring of the reductive group defined over K of the same type. We know that reductive groups are defined using some combinatorial data called root data. So, okay, next I'm going to talk about the quantum symmetric pair. So basically the input data is, we put another data. So firstly, we still have a complex connected reductive group G. Then we have some quasi-split involution. So quasi-split means that this involution, you can find some so-called anisotropic barrier. You can find some barrier such that the B and the theta B are in the opposite position. So you can say that you can show that such involution is more or less just some graph involution composed with some the Chevalley involution. So this omega in type A is just a conjugate inverse. So in general type, we also have such a thing. So this is the input data, and we can see that this theta fix your root lattice and weight lattice and covariant lattice, and we use this y upper I to denote the theta invariance of y, and upper lower y to denote the theta covariance. So basically, this after you input this data, you can define something called i-quantum group, this UI or quantum symmetric pair. So this i-quantum group is a subalgebra of the quantum group generated by these generators. So you can see this theta, this curly theta is just some parameters which you can ignore. So so if Q is 1, it's really just some Fi plus E tau I is something which is fixed on the theta. So I can show that this is a so-called co-ideal subalgebra. You apply the delta to this UI, you get the image as in UI tensor with U. This thing is called, this pair is, people call this quantum symmetric pair, and this UI, particular UI, is called i-quantum group, the I for involution. Okay. Right, so just like the canonical basis, one can also construct some wonderful basis for this i-quantum group, so-called i-canonical basis. This is constructed by Bao and Wang. You have this, so we are still considering the basis on this so-called modified unquantum group. You can do similar thing for this quantum group to get some modified quantum group and consider this basis. And you can also form this, you can show that this basis, if you consider the submodule considered spanned by this basis, is not just a submodule, it's actually a subalgebra. Okay. So this is so this thing also has some integral form inside. All right. Then we can do the similar thing. We just specialize specialize Q at 1. We consider this just the similar stuff. We consider this U dot IA, which is specialized by sending Q to 1. So A is any commutative ring with unity. You can also consider this A submodule, some kind of restricted dual, which is spanned by the dual i-canonical basis. So basically, you consider all the linear forms which are almost vanished everywhere except for vanish on every i-canonical basis except for finite ones. The theory is that this thing a priori is just some ring, some Z module, but actually it has a very natural structure of Hopf algebra. So one can see that this thing defines a Z group scheme. And moreover, if you consider the base change to any algebra closed field, here we assume characteristic is not true, then this algebra OKI is isomorphic to the coordinate ring of the symmetric subgroup G theta. So in particular, this OKI is reduced. So here, this G theta, abuse notation here. So basically, you know that the reductive group is defined, classified by some combinatorial data, which is independent of characteristic. So in this symmetric world, you can also classify such symmetrical pair using some combinatorial data, which is more or less independent of the characteristic, as long as your characteristic is not true. So here we get some, after base change, we get something which this symmetric subgroup of the same type as your input data. Okay. All right. So this is really just some starting point of the whole project. So basically, our initial motivation is to consider some notion called Frobenius splitting. It's some basically you consider a splitting of Frobenius map, just as the name suggests. So there's some you can consider this at least this the old stuff for quantum group we can consider Q specialized to 1. You get Chevalley groups, and you can also consider Q specialized to roots of unity, and you consider there is something called quantum homomorphisms. There are two maps which are due to Lusztig also, and the third one is you can do this. You can first if you can consider the things in the positive characteristic, you can first base change to the root of unity and then base change back to 1. Then you can show that this kind of thing, which is defined using quantum, this quantum Frobenius splitting will actually give you some splitting of the Schubert varieties. So basically here we are doing something similar. So at the end, we are able to study the geometry of the G theta orbits using this quantum Frobenius splitting of the quantum symmetric pair. So if you want to look at some details, there's a paper about this work. You can also directly talk to me. I'm happy to explain. That's